All right, let's do it. Okay, I get so pumped starting videos. All right, so we already talked about vocabulary about parallel, or not parallel. We talked about vocabulary when we have multiple lines and a transversal crossing them. Sometimes those lines are parallel, sometimes not. And that's what we're going to explore in this video is what does being parallel mean? How could we make as few assumptions as possible and then prove everything else, okay? So first we'll just really quickly review that angle vocab we're using. And then the big idea here is just if the two lines are parallel, right? So if I have two lines going in exactly the same direction in space, and then another line crosses both, right? So if it crosses this line, then it must cross this line in the exact same way, right? Because this line is going the same direction as itself, and the two parallel lines are going the same direction. So the difference between green direction and orange direction is the same because orange is the same direction as orange and green is the same direction. So the difference between those two same directions is always going to create the same angle, right? That's the biggest concept here. But then, I mean, if you look at it another way, right? If I undo all those crazy markings I just did, if you know any one angle at one of these intersections, like 10 degrees, I don't know why I love the number 10 so much. And so then this is 170, this is 10, 170. That was straight chapter 1. But now the big idea is if these lines are parallel, all of those angles are the same down here because we have the same intersection, right? If you remember no vocabulary, and that's all you remember is if parallel, then all of those angles are the same. That's it, right? That's the kernel of knowledge. The rest of it is just ways of communicating specific situations and scenarios. Okay, so review. Okay, lines do not have to be parallel to use vocabulary words here. Okay, it's the biggest common misunderstanding or assumption people make. Okay, corresponding angles, same place. My hair corresponds to your hair, even though it's very different. Mine is glorious and frizzy and part gray. It's amazing. So, but our hair corresponds, even though it's different, right? My hair's on my head, your hair's on your head, but they're in the same spot, right? That's what corresponding angles are. Alternate interior means we're in between the two lines, but on opposite sides. So these are alternate interior. These are going to be the two by far that you use the most. Corresponding alternate interior. That's why I did those two first. And then the two ones that we do less common are consecutive interior angles. When we get to four-sided figures, we use this a lot. Like trapezoids, parallelograms, rectangles, squares, rhombuses, etc. This is when we use it because you're inside a shape. There is no like alternate interior outside that we're looking at most of the time. We're looking at how do these two angles relate, and usually it's is there a 180 degree turn? If there is, they're parallel. But anyways, we'll get to that. But that's what consecutive interior or same side interior angles refer to. Oh, I deleted too much. Okay. And then we have alternate exterior. It's just like alternate interior, except we shift to the outside. Whoa, that's not a pen. I'm being crazy here. But instead you're on the outside. Still alternate, right? And so that's what we have down here. Okay, so let's jump in. So we're going to make one assumption together, okay? The one assumption, the obvious truth that we all agree, like, hey, this is true, right? We can't prove it, but we're all in agreement, like it's obvious. That one assumption is if two lines are parallel cut by a transversal, right? So again, like I was saying, a line is always going in the same direction as itself. That's the whole definition of a straight line in space in Euclidean geometry. And we come across two parallel lines that are going in the same direction as each other, exactly the same direction in space. Well, then the angles formed have to be the same, right? Because the two lines up here are going in the exact same direction as the two lines down here. So the difference between those directions is the same. Okay, that's the big idea. So if two lines are parallel, then corresponding angles must be congruent. That is the only postulate having to do with the parallel lines that we're going to assume. And then the other ones, the alternate interior, the alternate exterior, the consecutive, we can all prove based on this one assumption, this one obvious truth. Okay, so let's go ahead and do that. If you want to jump ahead to me doing more problems, you can, but I'm going to prove the three theorems right now. Okay, so first one, alternate interior angles theorem. That's going to be the name we refer to. In shorthand, it simply says if parallel, then alternate interior angles are congruent. Okay, I named it right here, I abbreviated it right here, and now we're going to go ahead and prove it, okay? So we start with A is parallel to B, right? That was given. I love flowchart proofs. Okay, and the one assumption we made, the one thing we have to go on, the one foundation is, if two lines are parallel, then we know corresponding angles are congruent, all right? I want to show angle 3 and 6 are congruent. That's the goal here, to show alternate interior. So let's start with either angle 3 or angle 6. So I'm going to start with angle 3. So we know from our one assumption we made that angle 3 must be the same as its corresponding angle because we have parallel lines. And so angle 3 here corresponds with angle 7. So we know those two angles are the same. Okay, so I'm going to go ahead and write that. So angle 3 is congruent to angle 6. That was by our corresponding angle postulate. Okay, and so now what could we do? Okay, well, 3 is the same as, I said 6. Oh, what a goof I am. Oh my gosh, I drew 7 and I wrote 6. I'm doing two different things in my head. So 3 is the same as 7. Corresponding angles are the same whenever we encounter parallel lines. That's the postulate we just made. But we want to get that 3 and 6 are the same. Well, look at this. We know also that angle 7 is congruent to angle 6. How do we know angle 7 is congruent to angle 6? Pause for effect. Wait for it. Vertical angle theorem. Right? Not the definition of vertical angles. That would be that from a point we have an angle formed and then its opposite rays form another angle, right? But the fact that they're congruent is a theorem that we proved together. So the vertical angle theorem states that. If you wanted to be super, like, not leaving anything out, you could always up here say angle 6 and angle 7 are vertical angles. And you could say that was given from diagram. You don't need to do this, but if you wanted to be really clear, you could establish that they're vertical angles, then say that means they're congruent. And now that we have 3 and 7 are congruent and 7 and 6 are congruent, that means angle, well, let's do it in order here. Angle 3 is congruent to angle 6. What lets us do that? Cannot be substitution. There is no such thing as substitution with congruence, but they're both congruent to 7, so they're congruent to each other. That's the transitive property of congruence. Okay, so that's a nice little flowchart proof. I'll do the next one 2-column, just to keep alternating between the two for those of you that like one or the other. But again, it's better to be adaptable to difference in our different situations, more flexible, do some mental yoga. Okay, so alternate exterior angle theorem says essentially the same thing. It says if two lines are parallel, then the alternate exterior angles must be congruent. So we start with the given that lines are parallel, and then we want to prove the alternate. I'm not going to go ahead and prove both, and I even wrote that up here, like, and you should really prove both pairs, but it's literally the exact same proof off to the side. It is kind of cool how they interrelate, right? Like you could use the same parallelness, and then some of the steps might overlap, but really it's just a repeat, exact same repeat with different numbers. So I'm going to do the same thing here. I'm going to scribble that out and say, let's just prove one pair, and then we would do the exact same proof a second time if we wanted both pairs. Okay, so we start with L as parallel to M, right? Well, that was our given. Okay, and what does that tell us? Well, again, our one and only assumption that we made was then the corresponding angles are congruent. However, we did just prove that alternate interior angles are congruent, so we could use that. Let's do that. Instead of basing everything on the corresponding, now that we have alternate interior angles are congruent, let's go ahead and use that, okay? We want to prove 1 and 8 are congruent. Well, guess what? If we want to show 1 and 8 are congruent, we could start with these two and then use vertical angles, right? Because we just proved alternate interior angles are congruent. Let's use that theorem. Let's package that sucker up by its name. Okay, so 2, this is what we're going to say. We're going to say angle 4 must be congruent to angle 5 because we just proved that. That's the alternate interior angle theorem. Okay, so then we go to 3. We go, how can we use that, okay? Gosh darn, well, we want to show that 1 and 8 are the same. Those are the vertical angles, though. So we need to establish that. So again, if you wanted, you could say angle 1 and 4 are vertical angles. given by the diagram. We can skip that step and just jump straight to, I know angle 1 is congruent to angle 4. Because it's the same reason, I'm going to do in the same step. Also, angle 5 is congruent to angle 8, right? Actually, you know what? Let's even be more elegant. This is a 2-column proof, so we can't follow the flow of logic. So if you kind of just vomit it all in there, then you don't get to see the step-by-step process. So let's just do one of them, okay? So 1 is congruent to 4 by the vertical angle theorem, okay? And now we can put these two together. And so what we get is, well, then 1 must be congruent to angle 5, right? That's the transitive property of congruence. You're starting to see which ones we use a lot, right? But we want to show 1 is the same as 8. But we know over here 5 and 8 are interchangeable, right? So let's state that, okay? Well, angle 5 is the same as angle 8. And again, that's the vertical angle theorem. Whoa, I said vertical 8, vertical angle theorem. And then step 6 then will be, let's put these two steps together, and we get angle 1 must be congruent to angle 8, and that's by the transitive property. So we could have gone so many different ways with this proof. I chose 2-column instead of flowchart. I chose to use the vertical angle theorem to get from parallel lines to angle relationship. I could have chose the corresponding angle postulate. It's really up to you to kind of explore what works best. Notice I could have thrown even this step and this step together since they use the same reasoning. I could have just said, 1's the same as 4 and 5's the same as 8, but that wouldn't have to me been as elegant. So that's why I brought things in step by step in what I thought would represent a clear proof. Okay, let's go to one more. Okay, so this one's the consecutive interior angle theorem. So this one's a little different because we have to develop supplementary. It's not as easy as congruence. Congruence is just that's the same as that's the same as that transitive property. Supplementary, we got to use some sort of definition, maybe even some algebra. So let's see what's the best scenario. Again, I'm not going to prove both, but as soon as you prove one, you just do the same thing again with different letters. Okay, so we're starting with L and M, and we want to get a relationship between 3 and 5. Okay, well, let's use the corresponding angle postulate this time. Should we do flowchart or should we do 2-column? Okay, I agree. Oh, I hear the chanting. I'm going to go with flowchart. Okay, so let's go with L is parallel to M. Okay, so that was given to us. Let me just make sure we got room here. Oh, yeah, we got tons of room. Okay, so we got that. Those are parallel. And I'm going to use the corresponding angle. We could use alternate exterior. We could use alternate interior. Any way you want to go here with a previously proven theorem or that one assumption that we made together. So I'm going to go ahead and say 1 and 5, right? These are corresponding angles, so I know those are the same. So I'm going to say I know that, go back to blue here, angle 1 is congruent to angle 5. Okay, so how am I going to use that? Well, what I really need to get is a supplementary relationship. Well, I know the relationship between 1 and 3, right? Because I'm dealing with 3. I have 1, so I want to use that relationship. So over here, I'm going to say angle 1 and angle 3 are a linear pair. Okay, and how do I know they're a linear pair? I can see that in the diagram. So that's given by the diagram. Okay, and what does that tell me? Well, I could go to a couple different things here. So the supplement theorem says linear pairs are supplementary. If we're on IXL, it says linear pairs sum to 180 degrees. I'm going to go straight there. I'm going to go the measure of angle 1 plus the measure of angle 3 is equal to 180 degrees. And so you could do this in 2 steps using the supplement theorem and definition of supplementary. I like IXL's very clear. Linear pair sum to 180, and depending on the book, they'll phrase this differently, right? And then what I've got over here, and I'm just going to spread this out a little bit for just balance. Whoa, I took some other stuff with me there. Let's try that again. Okay, so over here, what I want to do is I want to say, well, if I know these angles are congruent, I want to get to the world of algebra because I got algebra over here. So to get to algebra, I'm going to use the definition of congruent angles and get the measure of angle 1 is equal to the measure of angle 5. Okay, and so, oh, I never wrote a reason up here? What the heck? Okay, let's Let's put a reason there. Nice thing is I'm on an iPad, so I can just whoop-dee slide that down. And so the reason for that was I used the corresponding angle postulate. Okay, then I used the definition of congruent angles. Okay, well now I can substitute those together, right? I can put this one and this one together and replace that angle 1 with an angle 5. So I can go the measure of angle 5 plus the measure of angle 3 is equal to 180 degrees, okay? And let's look what we're trying to prove again. Angle 3 and angle 5 are supplementary. Oh yeah, there we go. So if we know they add to 180, well then that means that angle 3 and angle 5. Notice I swapped the order. It's because I want to match the thing to prove exactly, but the order wouldn't have mattered there. Are supplementary. And how do we get from an algebraic statement to a word statement? Well, that's always the definition of supplementary angles. Okay, and up here, I forgot to put a reason here. What let us get here? Well, that was the substitution. It was not transitive. Subtract, what the heck? I can't talk. Okay, substitution, property of equality. Okay, you guys, those are the 3 most important proofs. Here's one smaller one. We're not going to use it as often. I'll do this proof, and then from here we just jump straight into the homework. So hopefully you're starting to see how we use this. But again, the concept is, and I'll just scroll up to the top, right? The big concept, whoops, is if the lines are parallel, then all of these angles at the 2 intersections are the same. That's it, right? That's the big idea. All of the vocabulary is clearly communicating individual steps in a proof, but the conceptual big idea is if I come across 2 parallel lines and I know any angle in this top intersection, oh, here's 100 degrees, I know every intersection here, every angle up there, and I know every angle down here. That's the golden goose here. If that's all you take away, bravo, that's good. Okay. Let's go. Let's go down here. So we're going to do the next proof. This one's much lesser used. Is that a phrase? Much lesser used? Sure. Okay, so in a plane, if a line is perpendicular to one of 2 lines, then it's perpendicular to both. Okay, so we're given that P and Q are parallel, and they just threw out all the givens. That's a little sloppy, but okay. All right, so let's go with step 2, 2 column. This is good. 2 flowcharts, 2 columns. I'm going to use the fact that T and P are perpendicular, and I'm going to say, you know what that means? Well, that means that angle 1 is a right angle, okay? And 2, that's the very definition of perpendicular lines. Okay, you know what? I'm actually going to go to degrees. I think that'll be the cleanest. What do we think? Is that going to be the cleanest? Yeah, I'm gonna go to degrees. I just think so. The measure of angle 1 is 90 degrees. Okay, and that was the definition of a right angle. Okay, and the nice thing about proofs is everybody's gonna do a different proof, or at least they'll have their own flavor to it, and that's okay. Somebody watching this video might be like, tisk, tisk, tisk. I could have painted this brush more beautifully. Awesome. I want to hear that in the I want to engage in that. Okay, let's go to 4 here. Well, what else do we know? Okay, we know the lines are parallel. So what does that mean about angle 1? Well, it must be the same as angle 2. So let's state that. Okay. Now this is why I don't like they threw the given in, because now I'm not using it till step 4. But P is parallel to Q means angle 1 is congruent to angle 2. What tells us that? That's our corresponding angle assumption we made. So that's our corresponding angle postulate. Okay, so step 5 then, I'm going to go ahead and go to algebra. I'm going to say measure of angle 1 equals measure of angle 2. That's the definition of congruent angles. Okay, well now I can transitive this. If 2 is the same as 1 and 90 is the same as 1, well then I could just say that the measure of angle 2 is equal to 90 degrees. Again, that could be substitution, but I think more clearly that's the transitive property of equality. The real reason I'm practicing it is we use it a lot in congruence, and so I want you to get comfortable with it. Okay, so number 7 here is, what do we have? We have 2 is 90, and we want to show that T is perpendicular to Q, so I'm just going to say angle 2 is, and we're just gonna step these first 3 steps backwards. We're going to start with 90, go to right angle, then we're going to go right angle to perpendicular. So exact same steps in reverse. So is, I'm going to get rid of the is A. I'm just going to write that smaller so it fits, is right angle. Okay, what told us that? Well, to get from 90 to right angle, that's the very meaning of the word right angle. So that's definition of a right angle. And then how do we get to our last step that they're perpendicular? So T is perpendicular to Q. The way we get there is simply saying, well, that's the very definition of the similar word perpendicular. So that's the definition of perpendicular lines, okay? So there was a couple proofs for you to digest. I'm going to take a pause, jump back to Zoom, and I'll come back and just do a bunch of homework problems with you. All right, I'm back. Okay, let's do this. So we're just jumping into homework problems now. So whether, determine whether, sometimes, always, or never. I love these problems. Okay, so is angle 1 congruent to angle 2? So if we're given angle 1 and angle 2 are congruent, what would that mean? Like just testing in reverse. If we have those two angles are congruent, well, that would mean that we have a 180-degree linear pair and the two angles are the same. The only two same angles added to 180 are 90 and 90. So that would mean that the two lines are perpendicular. So really what it's asking here is, are these two the same? Meaning, are these two 90 degrees? Meaning, are these two lines perpendicular? And so, yeah, they could be. Sometimes, right? But is it impossible? Is it never? They're never perpendicular? No, they could be. And are they always perpendicular? No, not always. They're not shown. There's no right angle drawn or anything. So the answer there would be sometimes. Determine whether the minimum number of angle measures or the minimum number of angle measures you would need to find the measure of all the angles in the figure for exercise 1. Oh, I like this problem. That's why I put this in here. Good job, me. Oh, and I erased my writing there. Oh, whatever. Okay, so here we go. How many angles would I need to figure out before I could get every angle value in the picture? That is the entire big concept of this. If I'm given one angle here, from chapter 1, I know this is 80 degrees. I know this is 100 degrees vertical angles. I know this is 80 degrees. I know all of these as soon as I know one angle. But the entire chapter, this unit, chapter 3, is if parallel and transversal, and you have the same line and parallel, that means we have the same intersection. And so all of those angles are the same over here. So we have 80, we have 100, we have 80, and we have 100. So the answer here is we only need one single angle measure in this entire thing. Right? The caveat is if they give us the angle measure as it has variables in it, well, we need to lock down one known numerical value until we know all of them. But if they give it to us like in a 2x minus 1, well, if we have one variable, then we need one equation. So if they said this was 2x, we would need something else like this one is 3x plus 1, and that relationship, that one equation of two angles will be enough to solve for x. Then we could find every angle. So, but really, if we know one angle measure numerically, then we can find every other one in the picture. Okay, state the postulator theorem that allows you to state that 3 is the same as 5. Well, look, we are given two parallel lines here, and often extending the lines can kind of help. This transversal between angle 3 and angle 5 is right here, and so 3 and 5 are alternate interior angles. So that's the alternate interior angle theorem. It has some number, 3 point something, but using a clear name is much more useful, okay? All right, and then, oh, and just to restate, this one says if parallel, then angles, right? That's the idea. So if parallel, then alternate interior angles are congruent. Next video, we're going to do the converse. We're going to say, well, what if we encounter angles in nature and we want to find whether or not the lines are parallel? And that's what we're going to do in the next one. Okay, so in the figure, we got 3 is 110, okay? And we got 12 is 55, okay? Find the measure of every angle. Well, let's just fill in everything now. We could finish this entire diagram now. So if that's 110, then this is 70, this is 110, this is 70. Oh, and look, this line is parallel to this line along the same transversal. So we have 70, 110, 70, 110. All right, in a different color here, in the bottom, we have 55. So this one is, what, 125? 55, 125. And then again, because this line's parallel to this line and we have the same transversal that hits both, we know along that same transversal, this intersection must be the same as this one, okay? And so we know this is 55, 125. This is 55, this is 125. Notice though that these two intersections are not the same. That's because these two lines are not parallel. So they hit this one transversal in different directions, right? They hit in different directions, so they have different angles. You have one board and you have two saws in your hands and you just go willy-nilly with your chainsaws in different directions. The cuts you make are different, at different angles in different directions. That's why those two intersections don't match. However, if you've got two saws lined up in exactly the same directions, and it doesn't matter what board you come across, any tree fallen, if you go railroad track saws in the same direction, then you're creating parallel cuts. You're creating cuts of the same angles into that same board, okay? All right, let's go to the next one. Explain why you can conclude the angle 2 and angle 6 are supplementary, but you can't say, and this is really similar to the last one. I dropped this in because this is one of the most common errors people have. So this line is parallel to this line, okay? What that tells us is we know relationships along one transversal of that line. So we know things about angle 3 and 4. Those are supplementary, consecutive. Remember, that's consecutive interior angle theorem. That says if we have two parallel lines, that's what you start with, and a transversal, that you're making a 180-degree turn because you're going from same direction to same direction, but backwards. And so this angle here plus this angle here add up to 180. That's the idea here. But here's the thing people do wrong, especially when you have a quadrilateral. People assume that relationship is every pair of angles. That pair, this pair. They just start using it willy-nilly everywhere. You only know that when you're going between two parallel lines, right? So when you're going between this line and this line on the same transversal, then yes, angle 3 plus angle 4 are supplementary. However, you do not know that these two lines are parallel, so you do not know that along this transversal that 3 and 2 have any relationship. In fact, in the picture, it really looks like the lines aren't parallel. And so you absolutely do not know 2 and 3 add up to 180. Same, you don't know 4 and 6 add up to 180 along this transversal. But if they did add up to 180, that's the whole next video. If they did add up to 180, then those blue lines would be parallel, right? So this is going to be a both direction logic. But the key is you only know angle relationships between parallel lines. So if you have two parallel lines and one transversal, you know a relationship between these intersections. If you have two random non-parallel lines and a transversal, you know nothing about the numerical values between those two, right? And so that's what was happening here with 4 and 6, is you had two not parallel lines and you had a transversal going across, so you know nothing about how this intersection relates to this intersection numerically. Okay, really common mistake there. All right, so let's just do some algebra now with this. So we come across these two parallel lines. We've got one transversal that goes across, so we know this intersection and this intersection are the same. We need to solve for x and y. I don't want a system of equations, so I'm not going to set my 10x equal to this, even though they are alternate interior angles. This angle and this angle are the same. I just don't want to have to deal with a system of equations, so I don't want one equation with an x and a y. Then I need two equations with x's and y's to solve. So instead, I'm going to choose the relationship between the y's. So what's the relationship between this angle and this angle? Well, these two lines are parallel, so that's that consecutive interior angle 180-degree turn. So our relationship is the 8y plus 2 angle plus the 25y minus 20 angle adds up to 180. Right? Yes, you absolutely could have said 10x is equal to 25 minus 20. You just can't solve that for one solution without a second equation. And the second equation you would have to create would be 10x plus 8y plus 2 is 180. Because you go, okay, well, this and this are equal, and these two make a linear pair, and yeah, you could solve that system of equations, but that's not the elegant approach here that precisely gets right away to one equation with one variable. So I chose the better strategy here, and then we get, okay, so 33y minus 18 equals 180. That's 33y equals 198. That's y equals e. So let's see, that's 6 of those. Yeah, 6 of those, okay? And then it says find x and y. So now we could just plug this back in. And I'm going to erase all my sketch work here. So if we plug this back in, we get 48 plus 2, that's 50 degrees. Just to double check, I'll plug it in the other one. 6 25s is 150 minus 20, that's 130. Yes, those add up to 180. That's good, okay? So if this angle's 50 and these add up to 180, that means this one's 130. Or you could say it's alternate interior right here with this one along these parallel lines. So alternate interior angles must be congruent. So we get 10x is 130 or x is 13. Okay, so let's do the next diagram. Holy moly, look at all these parallel lines. That's groovy. Okay, so let's see. Again, I don't want to set up a y and x equation. Then I need a system of equations, so I'm not going to do that. I don't know any relationship between this one and this one because they're not along the same transversal. If I wanted to relate this intersection to this one, I would have to jump from this intersection along the transversal to here, and then along this transversal to here. And that's too many steps. I don't want to do that. Plus, I don't want to relate x and y together. So instead, what I'm going to do is I'm going to say, what relationship do I have between this and this? Well, along this and this parallel line and this transversal, those are corresponding angles. So my corresponding angle postulate says 4x minus 5 must equal 3x plus 11, or just like the common sense big approach here is, right? I have parallel lines, so this intersection is the same as this one along the same transversal, so I just set them equal to each other, right? So subtracting 3x from both sides, x minus 5 equals 11, adding the 11 or the 5, I get x equals, oh my gosh, I can't talk and write. I get x equals 16. Again, now it's asking for x and y, so I got to go back. I'm going to plug this in first. I like double checking that we got things right. So plugging it in, that'd be 48 plus 11. That's 59 degrees for this angle. Okay, we should get the same thing up here. 4 of those is 64 minus 5. That's 59. Good, okay. Those two angles did match. Well, then what's this angle here, right? Well, what we really have, just to draw a separate picture, is we have these two parallel lines, and then we have this one line going across. What's the relationship between this angle and this angle? Well, that's that 180 degree turn. That's the consecutive interior angle, 180 degree turn. So with those lines parallel, we know that those add up to 180. So rather than going to the variables, I'm just going to say this angle is 180 minus the 59, because we already plugged it in. So I know that angle is e minus 60, 120, so that's 121. Okay, so we got 3y plus 1 is equal to 121. Make sure I can read that. That's 3y plus 1, yep. And then minus 1, 3y is 120. So y dividing by 3 is 40 degrees. Okay, let's go to this one. Oh, classic. Oh, this stumps people. All right, there's so many different approaches to this. How would you do this? I would say pause the video and try and figure this out. We got this free floating angle 1. What's it doing? Okay. Pause for effect. Okay, now I'll show you two separate approaches here. Okay, so one approach over here is draw an auxiliary line or auxiliary line. I don't know how to spell it. I'm thinking it's like that. No, that's not right. Okay, something like that. And so what we mean, an auxiliary line, is just an extra line that didn't exist in the picture. And so what we could do is we started, notice these are parallel. So we started with parallel lines. So I could just add another parallel line here, right? And that's actually a postulate I forgot to add. Oh my goodness, that's in this section and I forgot to add it. Okay, well that postulate says given a line and a point not on the line, you can draw a line that is parallel to the first line passing through that point. So if I have a line and a point, I can say, yeah, I'm just going to draw a parallel line passing through that point. And think about it, right? I'm starting at that point, and what direction am I going in? I can go in any direction from that point. I'm going to go in the direction of this line. It's like shooting a laser. Of course you could do that, right? That's not a crazy assumption, so that's a postulate that we make. Whew, I feel bad I left that out now. I could edit this video, rewind, not going to do it. Okay, so we can add an auxiliary line. Now let's just add in the information that we have. Okay, so we have a 36 degrees here. We have a 31 degrees here. Well, we could just alternate interior angle this because I drew this line parallel. 31 degrees is the same as 31 alternate interior angle. 36 is the same as 36. That's alternate interior angle. And so you add those together and we get one large angle of 67 degrees, okay? So that's one way to do it. Another way to do it is somehow relate this, this top intersection with the bottom intersection. And you could do that by going like this. I mean, there's lots of ways. You could like draw a line here. You could extend this line. You could extend this line. So there's tons of ways to do this. I'm going to choose, whoops, let's just get green. Okay, I'm going to choose to extend both lines. Why not? I'm not going to connect here. I'm going to draw this line up here and this line down here. So this is 31 degrees. This is 36 degrees. And we're looking for this angle, okay? Well, again, alternate interior angles, because this line's parallel to this line. If that's 31, then this is 31 degrees. And oh, look, we have a triangle that adds up to 180. So we just go 180 minus 31 minus 36. So that's 180 minus 67. That's 120 minus 7, so 113. So we have this angle is 113 degrees. And then we go, well, these are supplementary. So we just go, this angle right here is 180 minus 113, which is 67 degrees. So we get this angle 67, the same either way. Either way, we added an auxiliary line. We either extended this or we drew a parallel line to the three lines right through there. Really cool problem. A tricky one, huh? Okay, so we're not going to do that many more problems. Oh, IXL proofs. We're just going to kind of do some algebra. I'll kind of rush through. But the idea here is just correctly using which intersections match. Okay, so I'm going to zoom in here after I write these. So angle 1 is 50 degrees. And angle 3 is 60 degrees. Okay, and then just find a bunch of stuff. So let's zoom in there, okay? And I'm going to go in green. If that's 50, well, then we know one. Whoa, let's go to thinner pencil now that we're zoomed in. So this is 130. This is 50. This is 130. Oh, these are parallel here. So I know along the same transversal. This is the same intersection. So 130, 50, 130, 50. Okay, and then we go over to the other one. Oh, wait a second. These are parallel too. So along the same intersection, this is the same up here. So I'm going to go ahead and do that. Okay, so this is 50. And then we have the same intersection here. So 50, 130, 50, 130. Same thing parallel. So this is 50, 130, 130, 50. Okay. Now, we don't know anything about these intersections. We know they're the same, but we don't have a single angle up there, so we can't do anything with those. Okay, let's go over to the right, and we'll do the same thing. Okay, if that's 60, then we have 60, 120, 120. This line is parallel to this line, so along the same transversal, we have the same intersection. So this is 120, 60, 60, 120. These two lines are parallel, so along the same transversal we get 120, 60, 120, 60. Same thing over here, we get 120, 60, 120, 60. Okay, but now we're stumped. How the heck do we get up there? It's an insurmountable mountain. Well, the trick is we have a triangle with a 50 and a 60 in it. Or, if you don't want that triangle, we have a big triangle that also has a 50 and a 60 in it. So either way, you go 50 plus 60 plus something equals 180. And so you do a little algebra. You end up solving that this has to be the 70 degrees left over, which then means you can solve all the missing angles up there. So this is 110. Here's 70, here's 110, and we could just finish all of these. We don't need all of them, so I'm not going to do all of them. But we do know this line's parallel to this, right? That's down here at the bottom. And so along the transversal, this is the same intersection. So 110, 70, 110, and 70. So that's how you could like jump around a big picture, and that answers all the angles that we're looking for. Okay, find x and y here. Let's look at this. So let's just fill in some angles here. I'm not going to solve all these rigorously, but the idea is all three of these are parallel, and there's one transversal. So this angle is the same as this one, and this one is the same as this one along that same transversal with parallel lines. And so all three intersections are the same. So all three intersections have 56, 56, 180 minus that is 124, 124. So that's all the angles at all of the intersections, right? So here's 56, 124. And up here is 124, 56. And so you can just do some quick algebra just to solve those. Over here, same thing, you have parallel lines. And so along one transversal, corresponding angles are the same. So this is 68, right? Along, wait a second. That is a cool problem. Are we getting a crazy scenario here? I'm liking this. So we've got to use a y squared here. This is beautiful. Okay, so anyways, let's go ahead and solve this. So 2x equals 68. So x equals 34. Well, now this isn't a variable anymore. This is a number, right? So 3 times 34, that's 90 and 12, so that's 102 minus 15. So that's 92, that's 87 degrees. Well, then how could we get this? Well, we have a triangle. And in this triangle, we have an 87, we have a 68, and then we have a y squared. So you could write an equation, but I think better is just going, well, what is y squared? So 180 minus 68 minus 87. So that's 180 minus 140, 155. So that leaves us with 25. So now we just have this last angle, y squared is 25. So y is plus or minus 5. Now, a lot of times you only take the positive value, but here, if I plug in y, a variable is -5, I still get a positive angle. That's okay. So actually, y is 5 or it's -5. Both are valid things. Whereas, if I got like the side of a triangle is y, and I do the same thing and I end up getting like y is 5 or -5, I could rule out the y equals -5 because the length of a side can't be negative. However, a variable can be negative as long as when I plug it in, I get positive values. The angle here is still positive 25 degrees, so -5 is a valid variable number, okay? All right, so here is that same scenario we did above. So I'm going to do these two differently. This one I'm going to do, I add an auxiliary line parallel to this, passing through this point. And so this being 37 means this is 37. This being 110 means corresponding angle 110. So then linear pair, this is 70. So add those two together, and 70 plus 37, you get a 107 degree angle. The other one, I'm going to extend it. Woof, I have to extend both of these a lot. Okay, there's my extension. Oh, and that's 90, so we know this is 90, right? And then along this, this is 157, so corresponding angle, here's a parallel set of lines, and so along the same transversal, this is 157, which means linear pair is 23 degrees, right? 23. So then we do a triangle, 90, 23, the leftover of 180 minus 90 minus 23, that's the same as 90 minus 23, that's 67 degrees. And then we go, oh, well then we just do 180 minus 67, and we get 113 degrees for 1. So you can either extend the side, or you could draw that auxiliary line. Two different strategies. Okay, I'm going to stop the video and jump over to IXL proofs. Alright guys, I jumped on IXL. I'm on D6 proving proofs involving parallel lines. So this is essentially the forwards. If parallel then, D7 is the converse, and that's what the next video will be on. So for this, let's start. So we start with parallel lines. We get then the angle SVU is the same as QSR, so that's this angle and this angle. That's our corresponding angles postulate, our one assumption. And then it says, okay, so we know that QSR and RSV add up. That's a linear pair, so QSR adds up with RSV. That's the one right next to it. So those add up to 180 degrees. That's the linear pair. And then what let us get to this? Well, I'm thinking from here, we probably use this statement too and substituted out the QSR for the SVU. So that's what happened here. So that would be essentially substitution. Although I would have had my students state that this is equal in algebra first before substitution, but I like it. Okay, let's hit that. Let's go to the next one. So we want to prove that these angles are supplementary. So if we get these angles are the same, so UXV are the same as RSV, this one. So if these two angles are the same, then how do we know lines are parallel? Oh, they went ahead and jumbled up the forwards and the converse. So this is the converse of the corresponding angle postulate. They mixed the two up. They didn't used to do that. It used to be separate, only going forwards. Okay, so we're starting here with parallel. That's correct, okay? Just to be clear, the converse is when we start with the angle relationship, and that implies the lines are parallel. That's what the next video is about. This video is all about we know the lines are parallel, then we can know information about their angles. So the angles are the same or supplementary. Okay, so let's do this. So if these are parallel, then we know corresponding angles match, okay? We have linear pair. This looks like the same as the first one we did. And so could we substitute out the TSV for the WXV? That's what happened, or WVX. That's what happened here. So that was substitution. Okay, we're going to hit enter there. All right, so complete the proof that these two angles are the same. Well, we have the corresponding angle postulate telling us RUV is the same as PSR, corresponding angles, and that's because the lines are parallel. Then we have PRS is the same as QRU. So this angle here is the same as this angle here, okay? And that's because vertical angle theorem. All right, so then what lets us say that RUV is the same as QRU? Well, that's because they're both the same as PRS. So that's the transitive property of congruence, okay? Let's do another one here. We're up at 60. This is getting a little more interesting now, okay? So we're given that, oh, this is the converse again. Psh, look at them mixing things up. So we'll just stop the video here. I'll do the next video, and then we'll come back. We'll do more proofs that kind of mix it all up. I hope you enjoyed it. Good luck, you guys.